Everybody. So, we were discussing psychrometric processes or processes involving moist air. Now, there we have seen one important process in which two streams of moist airs are mixing together. Let us say this is one stream and this is another stream. They are mixing adiabatically, that means there is no heat transfer with any external agency. Whatever energy exchange is there, that is only due to the mixing process, and then the resultant stream is coming out. So, basically what we do here, we do mass balance, obviously mass conservation has to be satisfied, and we do energy balance. Energy balance means again we neglect the changes in kinetic energy, potential energy, but we take into account only the change in enthalpy, because that is the main contribution towards energy content of the flowing air stream. And also we assume that during this process there is no condensation. So, doing all these things, we have got a few relationships. One is the total mass will remain constant, the total mass of water vapor that will remain constant, and from there we have got or we can get H3 if it is the enthalpy. Let us put 1, 2 and 3, and these symbols has got their usual meaning. So, H3 will be M1 H1 plus M2 H2 divided by M1 plus M2. M1 plus M2 is nothing but M3, all right. So, this we will get, then we will get W3 is equal to M1 W1 plus M2 W2 divided by M3, and we will get T3. This is not exactly equal, but almost equal. This is M1 T1 plus M2 T2 divided by M3. This is not exactly equal, but almost equal, so that for our all calculation purpose we can take T3 is equal to M1 T1 plus M2 T2 divided by M3. So, this I have derived in my last class. Actually, in air conditioning calculation, the type of precision we need there, we can go for this type of approximation. So, now if I want to represent this on a psychrometric plane, so we are having two conditions. Let us say this is 1, this is 2. That means we are having two samples of moist air and they are mixing together. So, the mixture condition one can conclude from this mathematical relationship that mixture condition will lie somewhere on the line joining these 2 points. Okay. So, that is very important and that is quite useful, that if you have got 2 points, then you can easily have the mixture point on the line joining them too, and then the point will be somewhere here, let us say. So, this point we can call as 3. Now, what is the relationship between 1, 2 and 3. The relationship between 1, 2 and 3 is like this. So, the ratio by which 0.3 will divide the line 1, 2 is like this. It is MA2 divided by, sorry, and this is MA1. This is how it will be divided. Well, here of course, please note down one thing that is important, and it is a slip of pen. See here M1, M2, M3, let me write M1, M2, M3 mass of dry air, because I have told that I am doing the analysis based on the mass of the dry air. Here actually M1, M2, so I can write M1 is equal to nothing but MA1, so M2 is equal to MA2 and M3 is equal to MA3. All right. So, probably I have used different symbol earlier, probably I have used MA1. So, here M1 is nothing but MA1. So, please note that. So, this is nothing but the mass of the dry air, because number of times I have told that the analysis is done based on the mass of dry air, not the total mass of the sample. All right. So, this is how we will get. That means, as it is being a triangle, triangle means if we have these two straight lines, one line dropped vertically from 1, another line extended horizontally from 2, then we will have a triangle. So, this will indicate the change in dry bulb temperature. So, delta T, this will indicate a change in moisture content or specific humidity. So, this is delta W, and this will indicate nothing but a change in enthalpy. And here also we can have similar type of a relationship. That means, all right. So, see this slant line is the change of enthalpy, because we have got enthalpy scale somewhere here. Okay. Somewhere here we have got enthalpy scale. So, this indicates the change of enthalpy, this indicates the change of specific humidity, and this indicates the change in dry bulb temperature. So, that is how the process will be represented. All right. So, basically what we can do, we can use this formula, or if we have a psychometric chart, geometrically also we can find out the condition of the mixed air stream. Now, if we see the psychrometric processes, then apart from mixing, there are two basic type of process. One, there is a change in dry bulb temperature delta T, this is delta H, and another, there is a change in moisture content or specific humidity. So, this is delta W, then in this case also we will have some sort of a delta H. All the processes, they are combination of these two basic processes. Okay. So, so let us see these two processes, and of course, there are a few exceptions where condensation etc. are taking place because part of the process is taking outside the saturation curve. We are not going into those complications. So, in general, most of the air conditioning processes or psychometric processes, they are different combination of these two processes. So, if we consider there is only change in dry bulb temperature, but there is no change in the specific humidity. So, one can write it like this. That means, in this, for this process W1 is equal to W2, all right. And in this case, whatever is the energy transfer, that is in the form of sensible heat. In the first case, let us say we call it process 1. So, in this case, whatever is the energy transfer, that is in the form of sensible heat. And we can write Q sensible is equal to MA. MA, I will write it in terms of H. So, I can write in terms of delta H. It may be cooling, it may be heating. So, that is why I have shown arrow on the both sides. Okay. So, we can write this one Q sensible as equal to MA into 1.005 plus 1.88 W into delta T. So, this is what I can write. And then again one can take this thing as an approximate specific heat for the moist air which I have introduced, and then that will be, I am not writing that, 1.02016 into delta T. That means, I am eliminating W. That means, please try to follow that. That means, what I am doing in that case, the sensible heat transfer I can calculate knowing only the temperature difference. I have not to know what is the specific humidity of air. Approximately I can calculate. Then there is another thing. Generally, for air conditioning calculation, we do not specify the mass flow rate of air, we specify the volume flow rate of air. All right. And there is one advantage for air conditioning processes, that the air pressure does not vary much. It is very near the atmospheric pressure. So, density is almost constant. One can, for all calculation, one can treat density to be almost a constant. So, doing all these things, one can write Q dot H, the rate of sensible heat transfer, is equal to CMM. What is CMM? Cubic meter per minute. Air flow rate, cubic meter per minute. Then density of air at atmospheric condition, 1.2 kg per meter cube. Then 1.2016 specific heat of moist air multiplied by delta T and divided by 60, because it is in cubic meter per minute. So, you will get ultimately one number which one can remember, 204 delta T. So, whenever there is sensible heat transfer only, we need not bother to know the condition of air. We can do an approximate calculation knowing only the temperature difference and using this formula. Well, I have missed something. So, CMM should be there.
This 1.2 is that we adding up those two.
See, actually you cannot add up these two. What you have asked is like this, that 1.2016 whether it is coming by adding up these two terms. Well, we cannot add up these two terms unless we know W or specific humidity, and for different specific humidity this value will be different. But I have told that the contribution of the last term 1.88 W is small. So, that is why one can make some average, particularly which will be suitable for almost all air conditioning processes. So, that is why we have taken one average value 1.2016. This is little bit approximate.
What is the 1.2?
1.2 is the density of air at atmospheric condition, 1.2 kg per meter cube. All right. So, should we go to the second process? In the second process, which is another basic process, there is only transfer of heat due to latent heat transfer, or there is transfer of energy due to latent heat transfer. Here also we can write that Q latent, we can write Q latent is equal to m dot A into delta H. So, obviously from enthalpy we can get that, but one can again do some sort of a calculation and one can write that this is nothing but m dot A HFGO W, well, let me write it in terms of delta W. So, this one can write, and again I will do the same thing. I am not going to write it, that means I will bring CMM, because in most of the air conditioning process the air flow rate is defined in terms of cubic meter per minute. So, I can write ultimately Q dot S is equal to, sorry, Q dot L latent heat transfer is equal to, doing all these mathematics. So, this is CMM into delta W. So, these two formula we can remember, that Q dot S is equal to 0.0204 CMM delta T and Q dot L is 50 CMM delta W.
So HF0 is that
The HFG0 is the latent heat of evaporation at 0 degree Celsius. Suppose we have got water at 0 degree Celsius and we want to get saturated vapor at 0 degree Celsius. So, we need HFG0, its value is 2501 kilojoule per kg per all right. So, up to this it is all right. So, let me write down these two. Q dot S is equal to 0.0204 CMM delta T. Q dot L is equal to 50 CMM delta W. All right. And then we can have any process which is a mixture of, where both change in dry bulb temperature and change in specific humidity is there, where energy transfer is due to both latent heat transfer and sensible heat transfer. So, we can write Q total is equal to 0.0204 CMM delta T plus 50 CMM delta W. So, this is what we can write. all right. Now, generally we define one quantity here which is known as sensible heat factor. Sensible heat factor. What is sensible heat factor? Sensible heat factor for any process is equal to sensible heat transfer divided by total heat transfer. So, basically we will have 0.0204 cmm delta T divided by 0.0204 cmm delta T plus 50 cmm delta W. So, this is your sensible heat transfer divided by total heat transfer, and obviously you can see cmm can be cancelled, dropped from both numerator and denominator, and of course one can divide it by 0.204 and get some sort of a simplified number, all right. So, one can have a representation of this process also on the psychrometric chart. You can do it easily. That means, let us say the total heat transfer process is something like this. Okay. So, this is the change in dry bulb temperature, this is the change in humidity ratio, and this is the change in enthalpy. Well, you see, this is the change due to, this is the change in enthalpy due to the change in dry bulb temperature. So, what one can write? This is nothing but sensible heat factor, and this is nothing but 1 minus SHF. So, this will be the ratio by which this total enthalpy will be divided. This can be a representation of our sensible heat factor. Well, so with this, let us slowly go into the air conditioning process with this background. Now, you see, well, before going into the psychrometric process of air conditioning, let me give little bit of the principles or what we want to do in air conditioning. Air conditioning, actually we are conditioning the air, and there could be different purposes for it. There could be comfort air conditioning, there could be conditioning of air for preservation of foods, etc. So, our concern is comfort air conditioning. So, actually we are going to consider comfort air conditioning. All right. Now, in comfort air conditioning, basically what properties of air we want to monitor. So, we want to monitor, actually let me give it in a system representation. Let us say this is conditioned space. So, this is a conditioned space. Here as input what I am sending is air. Air I am sending as input, and this air has got different attributes like temperature, like humidity, like dust, like odor, like it should have also some velocity. So, these are there may be a few more attributes or qualities of air, and as an output what I am getting is feeling of comfort. This is feeling of comfort, all right. Now, this feeling of comfort generally it is compared with some set feeling of comfort. Now, this is difficult because the feeling of comfort generally it cannot be defined in a very concrete manner. It will vary from person to person, even for the same person when he is well and when he is, let us say, suffering from fever. So, that will be different. So, but there are some set rules by which the feeling of comfort can be defined. So, that is why there is some set feeling of comfort also, and these two can be compared. So, this comparison can be like this, that one person is inside an air conditioned room or conditioned space. So, he has got in his system, he has got some feeling of comfort and he is not feeling comfortable in the room, and he can tell, okay, well, it is not comfortable. So, that is a comparison between the feeling of comfort and the set feeling of comfort. Or it can be like this, that it has been quantified, that we have assumed that in this room if we maintain 25 degree Celsius temperature, then everybody should be satisfied, but I am seeing that the temperature is 23 degree Celsius. So, then these two are not matching. So, if these two are not matching, then there will be a feedback feedback information. So, we will get the feedback information, and that will do some controlling or conditioning. So, this is control, conditioning of air. So, that will do the control or conditioning of air. So, that is how we can describe the function of an air conditioning system. So, basically we are supplying air to the conditioned space. The air should have some quality. So, these are like temperature, humidity, dust, odor, the velocity of air, etc. So, with this it is entering the room. In the room there are occupants, they will feel certain degree of comfort. That degree of comfort may not be equal to the set or desired degree of comfort. So, then there will be some sort of feedback information, and by which we will control the air. Okay. This is what is done in an air conditioning system, and basically as far as thermodynamics or heat engineering is concerned, basically one should be interested in temperature and humidity, but as a system engineer one has to look into all these things, that there should be filter for filter for separating the dust particle, there should be some method for cleaning the air from bad odors. Even there should be some technique for reducing the noise level, though it does not come directly in air, but well, people inside the room, they should feel comfortable. Okay. So, noise level should be within particular limit.
Ships this must. Passenger vessels is attenuated.
Yeah. So, attenuation of noise should be there. Means why only in ship, in suppose this room, they have taken special care for, I mean, to have a particular quality of, I mean, particular audio quality inside the room. Okay. So, there are, and this comes, sometimes this comes under the broader purview of air conditioning. All right, but mainly as far as this is a course in thermodynamics, we will mainly consider the temperature and humidity aspect. All right. Now, see again the temperature and humidity, these two we want to control, and the air which we are taking and supplying to the room conditioned space, that air we take from the ambient atmosphere. Now, the comfort condition or comfort feeling, the demand for comfort for human being, that does not change throughout the year, whereas the outside condition of air or atmospheric air condition of atmospheric air, that changes over the year. Seasonal changes are there and daily changes are there. So, obviously, our the methodology we will take for conditioning the air, that will be different at different time. Means we cannot have a set process by which always we can have conditioned air which will give me the desired comfort condition. All right. Broadly, we can divide the air conditioning requirement into two categories. One is your summer air conditioning and another is your winter air conditioning. And again, in summer air conditioning, we can have different summer conditions. We can have hot and humid condition and we can have hot and dry condition. Let us say desert condition which is hot and dry, and our tropical country, particularly like West Bengal, etc., northeastern region. So, you will have hot and humid climate. So, the techniques by which we will condition the air, that will be different in different cases. So, before going into the details, we should have some idea regarding the comfort condition. Means one can spend hours together on comfort condition, but I will just tell something that there are different recommended comfort zone. Means the air in the room, it should be within certain range of the psychrometric chart, or its temperature and humidity would be within certain range, so that average human being will feel it comfortable. Well, when nothing is given and this changes slightly from summer to winter, there are different norms given by ASRE. What is ASRE? So, that is a professional body which deals with refrigeration, air conditioning, ventilation, etc. It is America based professional body. Of course, it has got its activities throughout the globe. From different part of the globe, one can be member of it and can take part in different activities, but it is the global organization which is based in America for setting the norms, etc., for air conditioning and ventilation, etc. So, ASRE has got different standards. So, without going into details, because we do not have time, this is not a course of air conditioning. So, one can roughly take a few values, like universally this is assumed to be the accepted comfort condition, though it can change from application to application. The dry bulb temperature is 25 degree, sorry, this is 25 degree C, that is the dry bulb temperature, and relative humidity is 50%. So, if we do not have access to the ASRAE comfort chart, so we can take these values roughly, that it is 25 degree Celsius relative humidity, sorry, 25 degree Celsius dry bulb temperature and 50% relative humidity. Actually, one can change these values, they are little bit interdependent, means one can change the value 25 degree Celsius slightly. So, there will be some change in the relative humidity also. And summer and winter there could be some changes. As I have shown, these two are not fixed value. Generally, one can get a range like this, within which people will feel comfortable. Okay. So, why I have told all these things? These are important information, and at the same time, throughout the year, I will try to keep my room at 25 degree Celsius, 50% relative humidity. Throughout the year, I will try to do this. So, let us see how can we do it in summer and how can we do it in winter. In summer, the outside temperature, the air temperature, ambient air temperature is more than 25 degree Celsius, and its relative humidity is also, because if we take it as a hot and humid climate, so its relative humidity is also more than 50 degree Celsius. So, if we go for summer air conditioning, and let us say hot and humid climate, hot and humid climate. So, we have to cool and dehumidify the supply air. We have to cool and dehumidify the supply air. Now, in air conditioning, generally this is done by a single process. So, we are achieving both, please mind it, we are achieving both, we are achieving cooling of air, we are achieving dehumidification of air, but conventionally in air conditioning we achieve it by a single process. All right. What is done? We have got a cooling coil. Sometimes it is called dehumidifying coil also, or cooling and dehumidifying coil also. All right. So, the cooling coil, I am just showing it schematically. Actual representation is slightly different, but you can understand. The cooling coil is a tube like this, schematic representation of this cooling coil is like this. So, through this I am sending cold refrigerant. Basically, this is nothing but the evaporator of the refrigerant. And this coil, with this coil, for better heat transfer, we are having outside the coil, we are having fins. So, it is in most of the application, it is a finned coil. And then refrigerant is passing through this. While refrigerant is passing through this, refrigerant is evaporating. So, it will absorb air, it will absorb heat and absorb heat from the flowing air. This is air, hot and humid air. Then when air will come out, it will be cold and relatively dry. Relatively dry air. So, cold and relatively dry air will come out of it. Cold, we can understand, it will become cold because the refrigerant which is passing through it is having a much lower temperature, but relatively dry, how? So, for that the temperature of the cooling coil should be so low that it should be lower than the dew point temperature of the incoming air. If it is lower than the dew point temperature of the incoming air, then what will happen? I mean condensation of or partial condensation of the moisture content that will take place. So, certain amount of moisture that will get separated. You will get moisture separated from here. So, you will find, if you see the practical construction of cooling coil, so with all the cooling coil there will be some drip pan below it. So, where the moisture in the form of water will be separated and collected and drained. Alright. So, this is the process by which we will achieve cooling and dehumidification.
What is the exact level of humidity controlled?
Can you repeat the question once again?
After it passes through the coils, cold and relatively dry air comes out.
Yeah.
But suppose I need a particular value of humidity in the air. Will that be separately controlled?
I will come to these issues slightly later on. I will come to this issue slightly. See, what you have asked, that how exactly the humidity will be controlled. So, I will come into these issues slightly afterwards, but one thing I will tell you, that for general comfort air conditioning, we can allow certain range of humidity. It is not exactly at 50%, it can be 55% or 50 to 60% like that. So, we can have a range of humidity. Okay, it is not exactly, but there are certain applications like electronic industry where chip fabrication is taking place, or some sort of photographic processing. So, there the humidity has to be controlled at a very close level, low humidity. There are certain processes where we need high humidity also. So, in those cases special measures are taken, but for general comfort conditions we need not go for a very precise control of humidity. There we should operate within a range.
So, this process we are having in control air dryers.
Yeah.
We are using control air, same process we are
Yeah,
using.
yeah, yeah. So, cold and relatively dry air. Now, you see, forget about the air passing over the tube. So, this through the cooling tube, cold refrigerant is passing. So, you will find that the tube surface temperature, that is also very low, and it is as low, it is so low that as soon as air comes in contact with it, I mean air becomes saturated and separation of moisture takes place. So, as soon as it is exposed to air, you will find that water droplet are forming on it. Okay. So, the surface temperature is known, surface temperature of the cooling coil is known as apparatus dew point temperature, ADP, apparatus dew point temperature. This is known as apparatus dew point temperature, the temperature of the surface of the cooling coil. Okay. Now, with this definition, I will go to psychrometric chart. So, this is our psychrometric chart. The apparatus dew point temperature is somewhere here. So, I call it ADP. I have explained what is ADP. Is not it? I have explained apparatus dew point temperature. You see, the air, ambient air is somewhere here, and apparatus dew point temperature is somewhere here, because at this condition if air comes, it will be saturated and its temperature will also be low enough. Now, the air, again let us go back to this, air when it is flowing through the coil, we cannot expect that the entire mass of air will come to apparatus dew point temperature. If we want to have the entire amount of air to come to the apparatus dew point temperature, then it should have, very large time of contact with the coil length should be very large, almost infinity. So, that is not possible. So, obviously, when the air will go out, its temperature will be lower than the supply air temperature, but its temperature will be higher than the apparatus dew point temperature. Okay. So, there will be some lowering of the humidity content, but it will not be as low as the humidity content corresponding to apparatus dew point temperature. What I mean to say, that we will have the condition somewhere here, means I do not know whether we can, this is not a very good diagram I have drawn. Well, let me draw another diagram, because what I mean to say, that if this is bit exaggerated for understanding. So, this is your ADP, apparatus dew point temperature. This is the SA, supply air condition. Then we will have the air which is coming out of the coil, that will be somewhere here. Okay. That will be somewhere here. Now, this particular aspect is described in a different manner in psychrometry. Okay. Is it understandable that if it is our apparatus dew point temperature, this will be the supply air condition? Actually, supply air condition means, let us not write it supply air condition. Let me again OA, outside air condition, and let us call it supply air condition, because this is supplied to the room. SA, supply air condition. So, this is actually supplied to the room. All right. So, it will be somewhere on this straight line joining the outside air condition and ADP, apparatus dew point temperature. Now, this phenomenon in terms of psychrometry, it is explained in a different manner. It is like this. What we assume, if you see the diagram here, what we assume that the air which is flowing over the coil, that is only a part of it is contacting the coil and coming to the apparatus dew point temperature. We assume that the air which is passing over the coil, only a part of it is contacting or in perfect contact with the coil and coming to the apparatus dew point temperature, and the rest of it is not at all contacting the cooling coil, it is bypassing the cooling coil. So, the process which has been shown by the psychrometric chart on the psychrometric chart here, it is idealized like this, that part of the air is in perfect contact with the cooling coil and part of the air is totally bypassing the cooling coil. Actual process is not like that, that certain air particles, they are close to the cooling coil, so they will have a lower temperature, then they will have again energy exchange with other air particles. So, it is like this, but we want to idealize the process like, and with that we want to introduce one factor which is known as bypass factor. So, bypass factor I will explain in our next class. So, this is your bypass factor which I will explain in the next class. All right. So, let us stop here.